Is there another kind of security? There's another kind of security. We're just talking theoretical here. Absolutely safe. But in fact, any of our theories, theoretical product. It is always through practical application. It reflects the characteristics of the product itself. Or is it functional purpose? That's like this one in our house. This is the same as some electrical appliances. No matter how well you protect it, why is there always some inexplicable state? It makes you careless. This so-called in-case situation occurs. What should I do at this time? This time. It is necessary for us to consider this safety. Under the premise of this safety, we need to do some mortgage in case. Even if you accidentally do it, this structure can also ensure your safety. Just like our plug, we made some triangular plugs. You can rotate this triangle 180 degrees. You will have several opportunities to plug in. But let's say I made a triangular socket here. Okay? But I'm going to plug it in through a triangular plug. If my triangle is an equilateral triangle, I can plug it in. I spin once, twice, 3 times. Right, so I need to do something. I do what's called disaster prevention. Only when the bottom touches the bottom. Can he plug it in? And this is a design. We call it disaster prevention. The so-called anti-fool is to prevent idiots. Any fool can do it. Anything can be done. What's the other one? Another kind. Are they some of the security risks we are involved in? Our connectors are usually like this. A structure of. We only talk about one. Usually a structure like this. This is the terminal. Right. It's an insulator. So when our relay is energized, this terminal is powered. Under certain conditions, we are likely to be operating. You might accidentally touch it. An application under high voltage and high current. It's an app security risk. Storage of various aspects. As long as it is this high power, there will be this phenomenon. So we did this design. What will happen to us? Just to avoid touching me. Touch me still makes it safe. How about that? I will add another insulation on it, so-called anti-shock. Of course, I'm exaggerating a bit. It's actually an insulated one, something similar to it. And what does that do? The effect is that I met someone. It touched this insulator instead of this conductor. Then this conductor, only in true. In the process of interworking connectors, it acts as a conductor. What about this structure? We also refer to it as being related to security. It's a kind of structural design. This is because you have this application requirement. There is this so-called security risk. So we have to make such a structural consideration. Is this the second type? Electrical related to electrical junctions. Electrical safety related. So there we are. It's also about electrical reliability. So what is reliability? Reliability. I told you about that. It's what I work for a long time. Throughout the life cycle of long-term applications, during the entire life cycle of the product, can always be stable and safe output. For example, a lot of our things are powered on. We have some electrical appliances at home, like a refrigerator. We'll use a plug-in board to power up the washing machine, but earlier, we have a lot of plug-in boards at home. It's low power. When my refrigerator and washing machine are plugged in at the same time, my entire patch panel, because this current is relatively large, so it starts to heat up. But what? If you only use 5 minutes, 10 minutes, no problem. This wire, this dining board, it's barely holding up. But if you keep using it for 5 hours, 10 hours, sorry, this patch panel, it may overheat, melt, and burn. It's a question of reliability. This is a classic reliability problem because our electrical appliances are, as long as you use this so-called strong electricity, this stage, it must accompany the temperature rise problem accompanied by so-called high currents. This is a classic example of this reliability problem. What about this question? Well, how are we going to solve it? First, we go through the materials, right? This is material. What is the second one? You have to have structure in place to prevent that. Lower the temperature. Okay, what about the other one? What about the other one? For our application, all our linear applications, it's divided into two very distinct lines. The first one is called static applications. I just stuck it there and didn't move. For example, the charging head of our mobile phones, plug it in there and charge it at night. It's almost motionless. This is a very typical. There is another kind. It's a dynamic application. And the application of this dynamic is simple. For example, our high-speed train, like the cars that we drive. For example, our satellite rockets and so on. This application in motion. How about this reliability? It's not a structure. It's not a feature. Broad. It's made up of multiple structures. A combination of features. It must be explained here. We connect its functional purpose. The functional purpose of the connector. It always, what it produces is a connection. This is its only and the only thing that matters. So all our security is fine. Reliability is good. It all revolves around the nature of the connection. So there's a problem. Or there it is. Reliability. Or security issues. That's also about connectivity. A short circuit. It's a connectivity issue. Open circuit. Is it a connection problem? There is a problem with our connection. Or is there no signal? Or the signal is shorted. Well, that's for this phenomenon. Something in between. For example, in the connector we have been talking about for a long time. It has a special. It's called a sequential. We learn this. This electronic physics. We all have it. There are such. All our connections. Does it come in the form of a signal? It's kind of like a wave. Or a continuous this. This signal energy conversion. That. If you look at it as a microscopic world, it's actually in an infinitely small amount of time, through an infinitely small energy, or through an infinitely small signal. You can make slices. Suppose we could slice time into infinitesimals. That's probably such a state. So under dynamic conditions, will it? Our connectors usually look like this. Such a terminal. Such an intermatch of a male and female terminal. What about this mutual cooperation? All its signals, all originated from, at the male and female terminals. This is called the contact area, this interval. So there it is. A structure of. How can we ensure the long-term sustainability of this structure? Continuous reliability. That is to say, how can we ensure the long-term sustainability of our signal communication? How reliable is that? This involves, first, will I be tired of this? It's an elastic structure. It's an elastic, demineralized structure. Will it cause fatigue? Will it fail? Failure is good. So at such a microscopic contact with the interface. And here we see a microscopic contact like this. The interface of it actually looks like this. We appear to see two planes. But what it's actually looking at is the microscopic level. It's two peaks touching. Then this contact, the area of contact, and its contact signal. Does it always meet my requirements for electrical performance? It involves. For example, we talk about the positive force, receiving resistance. So why am I talking about contact resistance? All of our stuff related to electrical signals, it has one of the most critical is the contact resistance. The higher your contact resistance. Does it mean that your contact is worse? Of course. If we generate one here, very high signal requirements, the integrity of the signal is very demanding. Then the contact resistance requirements in this area are very small. The contact resistance, the contact with you, it has a very strange phenomenon. That is, when your contact resistance is positive pressure and your contact area. It's a positive correlation. The more contact pressure you have, the more contact pressure you have, the lower your contact resistance is. No, this is reverse temperature. The lower the contact resistance, the more contact pressure you have, the bigger your footprint is. The lower your contact resistance is. I spelled this symbol wrong. It has such a correlation. Okay, so these things. It needs to be achieved through our structure. This is not something you talk about. I can do it however I want. How do you keep your volume fixed? In a fixed space. Make your contact resistance bigger. Make your contact resistance smaller. Make your contact positive. The contact area with you increases. This is all achieved through structure.